section 5.2.2, which is defining the inverse of an exponential function. So in the last section, we learned just briefly about the log equation and what it looks like, and then figuring out that a log equation is in fact the inverse of an exponential. So for problem 68, this is called the silent board game, but what you're going to do really is copy this table in your notebook, and then you are going to fill in the missing pieces. So in other words, how am I getting from 8 to 3? How am I getting from 1/2 to -1? So there's not many ones that they give you. So but most of us can probably kind of figure out the pattern pretty quickly, and then you'll fill in the table. So keep in mind we're working with exponentials and logs, so it's probably going to have something to do with that. And then for part A, you're just going to describe an equation that relates x and g of x, so that's coming up with the pattern. For part B, you're looking back at problem 57, and if you have not done so already, use the idea of the ancient puzzle to write an equation for g of x. Part C, why is it difficult to think of an output for the input of 0 or -1? And then D, find an output for x equals 25 to the nearest hundredth. So go ahead and do that, and then go ahead and push pause and do this problem. Okay, so you guys should have finished 68. So I wanted to talk about part C. Why was it difficult to think of an output for, or an input of 0 or -1? So keep in mind, the equation is really 2 to the y equals x, or log base 2 of x equals y. So what this is saying is 2 to the what power gives us 0? Well, nothing. There is no 2 to any power. Really, any number to any power is not going to give us 0. Same thing with a negative number. We can't get an out, or in this case, I guess it would be the input. We can't have a negative number. So no number to a power will give us a negative number. So that's important, and it's going to come back again. So just kind of keep that in mind. So for problem 69, this is another logarithm table. So you're going to be working with the log base 5 of x. It says she thought she could use the log button on her calculator, but when she tried to enter 5, 25, and 125, she did not get the outputs the table below displays. She was fuming over how long it was going to take to guess and check each one when her sister suggested that she did not have to do that for all of them. She could fill in a few more and then use what she knew about exponents to figure out some of the others. So what you're going to be doing is, of course, filling in the table. So for the table, you're using the equation g of x equals log base 5 of x. But it's kind of hard for us to think of an equation like that. So I always like to rewrite it in an exponential form. So really it's 5 to the y equals x. So you're going to raise 5 to a power of y, and that will give you x, which is technically your input. So just keep that in mind. And then you are going to use a calculator to estimate the remaining problems. So like 5 to the power of what will give me 6, for example. And then for part C, what do you notice about the results for g of x as x increases? So in other words, is g of x increasing or is it decreasing? And then you are going to draw a graph of the situation. And we have drawn a log graph before, so we should kind of have the idea of the general shape. Remember, it's essentially like a sideways exponential. Okay. For problem 70, so you can go ahead and pause me and finish that. For problem 70, it says to find each of the values below and then justify your answers by writing the equivalent exponential form. So we are going to just do part A together. So log base 2 of 32. So what that's saying is the answer is going to be, what is the exponent? So 2 to the power of what gives us 32? And it's going to be 5. And then what they also want you to do is to rewrite that as an exponential. So then you would write 2 to the 5th power equals 32. So you're going to go ahead and do this for parts B through H. So you can go ahead and pause and complete that. Okay, so 71 we are now on, so you should have completed everything else up till this point. So 71, it says, while the idea behind an ancient puzzle is more than 2,100 years old, the symbol log is more recent. It was created by John Napier, a Scottish mathematician in the 1600s. Even though that's not very recent, but it's okay. Log is short for logarithm and represents the function that is the inverse of an exponential function. You can use this idea to find the inverse equations of each of the following functions. Find the inverses and write your answers in y equals form. So when you are doing these problems, a trick, or not even a trick, but kind of the procedure of doing it is you want to rewrite it in the other form, because obviously the inverse of a log is going to be an exponential, right? The inverse of an exponential is going to be a log. So that would be your first step. So you're going to rewrite it in the other form. So we are going to do part A together. So we have y equals log base 9 of x. So my first step to find the inverse is to write it in an exponential form. So 9 raised to the y equals x. So remember, when we find an exponential, you solve for x and then you switch x and y. Well, we already solved for x, right? It's already solved. So all we would have to do is switch x and y. So it would just be 9 to the power of x equals y, and then that would be your answer. So you're going to go ahead and do B, C, and D. So you can go ahead and pause me, do those problems, and then push play. Okay, so our last problem here is 72, which says to practice your logarithm fluency by calculating each of the following without changing the expression to an exponential form. So in other words, you're just thinking like 7 to what power is 49? So A is obviously very easy. So I'm going to go ahead and jump to C. C is interesting because it's log base 5 of 5. So what actually happens is this 7, we can think of an exponent. You actually want to move it to the front. So this is really 7 times log base 5 of 5. And log base 5 of 5 is 5 to what power gives us 5? 1. So it's really just 7 times 1 equals 7. Now, that's like the complicated way, but I'm just kind of showing you why that works. But another way you can do it is anytime you have log base of a number to the same number, it essentially just cancels out. So it would just be 7. On the right side here, I was just really showing you why it works and how it works. So you guys will go ahead and finish 72. And then after you do that, you will do the math notes on logarithms and their notation, and that will be all.